So we are needing to talk more about projectiles. We started projectiles last week where we were talking about motion in two dimensions, and we talked about relative motion, and we introduced projectiles, and I said, hey, today is going to be a lab on projectiles. And that is true, but there's a little bit more theory we should discuss before we do that lab. So I want to do that now. I'm going to talk about the theory. I had, just to clear this up, make sure no one missed my announcement. I had said that we would do a quiz, but I changed my mind because I think what we'll do instead is on Thursday, we'll do a class group activity for relative motion. I think that's going to be a better way of doing it. You guys can kind of work out relative motion together because some people tend to find that easy and intuitive, and those people tend to be good with vectors. And then some people find it very challenging. So I think the group dynamic is just going to be better. So we'll do it that way. But for today, it's all about projectiles. So we talked about not just projectile motion last time, but also relative motion and just motion in two dimensions. So I should have put that on here. But we also covered relative motion and just 2D kinematics generally. These two are applications of kinematics in two dimensions. We will look now at more projectile motion. Oh, I'm sorry. I really didn't update this at all. And hopefully we'll talk about relative motion together with projectiles, but we will not be able to get onto forces today, I don't think. So we're going to pick up forces on Thursday. We'll do the relative motion group work as kind of a review. And then we're going to move on to forces, and forces and Newton's laws are going to be the main thrust of what we cover on Thursday. Okay, so here we have two equations that we derived last time. We have the time of flight and we have the range. So I hope you guys remember that we did find these equations. What case were they true for? Do you remember what constriction we had when we derived these equations? What was the... We had just an acceleration due to gravity downward. That was it. But there was something else too. For this to be the time of flight and the range of a projectile, it was something about where it ended up, where the projectile ended up. Do you guys remember?
Was it as long as v initial was equal to v final?
So in fact, the initial speed and the final speed will be the same. So that's true. Their direction will be different, the velocities will be different, but you're right, the speeds will be the same. Is that enough of a constraint? I believe it is. I believe that's enough of a constraint. That will do. That's not how I phrased it, Andrew, but you're right. Yeah, that's the constraint. What I said was it has to land at the same height it was launched from, but I believe if you just say that the speed is the same, that also forces this condition. I believe that forces this condition. So what you said is also correct. So yeah, that will work. But what it means is that, if I launch it like this and I let it go somewhere below where it was launched from before I say that it landed, then these two won't work. And Andrew's condition will not be true. The speed here would be less than the speed at landing. Does it make sense?
Yeah, because it would have gravity acting on it for longer. And it will be, yeah, so the acceleration between this point and this point has relatively less time to act. So the change in velocity will be less, whereas between here and here, it will have more time to act. The change in velocity will be greater. So yeah, it would be moving faster. Okay, wonderful. Hey, this is good. Good. Actually, let me scrub this part out because I don't want this part to be confusing. So yeah, so we're going to treat it as though it has some, oops, don't do that. We're going to treat it as though it has some particular launch speed. In the textbook, isn't it V0? I want to think the velocity vector is V0. And then here, you could think of this as being V final, and the speeds are what would match here as well. So I think I should have written this as 0 and 0 rather than I, but I mean the same thing, just the initial speed. Okay. Any questions about these and where they came from? No, everything good? All right, awesome. So let's press on and think about the consequences.
So I think we said this last time, right? We said what angle would maximize the range of the projectile, and you all told me that it would be 45 degrees. Am I right? We did talk about this, right? Yeah. So if we plug in 45 degrees right here, then we're finding the sine of 90 degrees. The sine of 90 degrees is 1. So the maximum range in this case ought to be v squared times 1 over g. Well, that's just v0 squared over g. Okay, the initial speed over g. So that's how we can maximize the range. If we choose other angles, we will get something different. Okay, so bear this in mind for the lab today. What happens though if we had air resistance? Here in this plot here, the parabolas are symmetrical. The only influence is an acceleration due to gravity. That's it, nothing else. But we could say, well, what would happen if we included the effects of air resistance? Okay, if you are very familiar with sports, you might know that like things like the longest range of a football pass, for example, you don't get with a 45-degree launch. The deal is that air resistance changes this picture and makes it a little bit more complicated. So when you have air resistance, you no longer have those symmetrical parabolas anymore. Instead, you get shapes that are kind of like this. And what you can see is that in practice, a 35-degree angle might go farther than a 45-degree angle. Okay, so a lower angle might do better. The effect of the air resistance is sort of to, well, it looks like it kind of shaves off some of the distance on the far side of the parabola. It just can't quite go as far. Dealing with the air resistance, though, is pretty complex because the force is opposite the direction of the velocity. So if you think about it, that means the acceleration would be constantly changing all the time in response to how fast the particle is moving and also what direction it's moving in. So solving for these sorts of shapes is not so easy. It's usually done numerically on a computer. We won't be dealing with it in this course. I just want you to be aware that, if I'm saying that 45 degrees gives the largest range, I'm saying it in the absence of air resistance. Okay, it can be more complicated in real life.
The physicist's favorite environment.
Right.
Airless, frictionless environment.
Airless, frictionless, and all cows are point masses. Yeah, exactly.
Yeah, spherical cows.
So we want to find now, say, maybe the maximum height that the projectile reaches. We already found the time of flight and the range. This is one more thing we could find. Now, this works if we land at the same point we launched from, but it also works if we land somewhere else, because we're just going to find the maximum height above where it's launched. So if we look at where it's launched and we want to find the maximum height from the launch point, this will work even if the particle hits a wall right here and doesn't come all the way back down, or even if the particle falls into a hole, that's fine. That doesn't change how high it went before that moment. Okay, so this is a more general thing. We're going to find the maximum height that a particle gets to relative to its launch point, We're going to call that maximum height h, just like in the diagram here. Okay, so this is v0, this is theta 0, the initial launch angle. Let's assume that we know v0, this launch speed. We know theta 0, the launch angle. So in fact, we know the initial launch velocity vector. And we want to find h. How might we do that? How could we find it?
Do we know the time?
So we don't, but we could find it, I suppose.
Is it v initial squared of the y direction divided by 2g?
V initial squared. So okay, yeah. So look, hey, wait, but how am I going to derive this thing? How do you derive it?
From the v squared is equal to v initial squared plus 2a times displacement of y formula.
Yes, beautiful. So I can start from here. Okay, I'm going to consider going from this point O to the point A. Okay, so I'm going to go from O to A. When I go from O to A, the final velocity here is 0, right?
Also in this scenario, a sub y is equal to minus g. So I'll plug that on. Oh, sorry, this should be delta y for the moment. Delta y is going to be h though when I go from 0 to a. My y coordinate is changing by an amount plus h. It's adding on h. So I have 0 is equal to v0y squared minus 2gh. And what you can see from rearranging, bringing the 2gh to the other side, and then I divide by 2g, is that I do get v0y squared over 2g. So this is one way to write the maximum height that it would reach. And the other thing we can do is we can plug in what v0y is. What is v0y in terms of these things? Oh, Aisho, thank you too. I only just saw your message, but yes, thank you, thank you. Yeah, V initial times the sine of theta, thank you. So remember, we could always find it by drawing the triangle. Let's just draw the triangle real quick because it never hurts to draw a triangle. This side here will be V0y, this side here will be V0x. This is the angle we're looking at, theta 0. V0y is the opposite side, so V0y would equal V0 sine theta. Okay, never hurts to draw that triangle. So I can replace that here and I get V0y squared. Oh, sorry, not y. I want to just find V0. V0 squared sine squared theta over 2g. So that's another way I can write it as well. Either way is correct. Now, you could find the time. I just want to point this out. You could find the time to go from 0 to a and do it from that. That would also work. It's maybe one more step, but it works fine too. Okay, let me bring up the pretty Persian version here. Okay, so those are the same equations I just wrote down. So this is another equation we can use and is sometimes helpful for figuring out, how high the projectile will get to. You can see here that changing the launch angle does give different heights. Okay, so imagine for all of these cases that the launch speed is the same. So in all of these diagrams down here, V0 is the same. But we are varying theta, the launch angle. And so when we vary theta, then we get these different paths. And so you can see that the ones that have the larger angle go higher. It does make sense because what you're doing is you're just changing, instead of shooting the projectile, shooting the projectile out like this, you're just taking it up and shooting it higher and higher and higher. So it makes sense. You increase this one, then you should increase the height, assuming you're holding everything else constant. Okay, so we're thinking about increasing theta. I'm just going to quickly sketch sine theta. This is theta, this is sine theta. The range that we're really interested in is just 0 to 90 degrees, a launch angle that's horizontal up to a launch angle that's vertical. And by the way, if the launch is below the horizontal, you can treat that as a negative launch angle. That's fine. But then the maximum height is the launch point. So that's kind of boring. So we're really looking here at 0 to 90 degrees. And what you can see is as I go from 0 to 90 degrees all the time, sine theta is also increasing. So by increasing theta, I increase sine theta. By increasing sine theta, I increase the height. You can also see how the ranges come out here as well. Okay. So let me ask you a question. 3 projectiles, and we'll answer it on Mentimeter, so let me put the code up real quick. It will be for today 7359416. Okay. 3 projectiles, A, B, and C, are launched with different initial speeds. Okay, in that last picture, they were all launched with the same initial speed. Here, they're launched with different initial speeds. Different initial speeds, so they reach the same maximum height as shown.
list the projectiles in order of increasing time of flight. So you're thinking the shortest time of flight up to the longest time of flight. That's how you're going to sort it, A, B, and C, however it goes. Okay. So they're all going to reach the same height. And we want to know which one has the shortest time of flight up to which one has the longest time of flight. Okay, some folks are already able to answer, but for those who are hesitating, let me make a suggestion. We have a formula for the time of flight. We have a formula for the height. Look at those two. We have a formula for the maximum height a projectile reaches and a formula for the time of flight. Look at those formulae. See if they show you anything interesting here. I'm going to even just write them down right here. So we just derived this one. And the time of flight one we had before, I believe it was, am I right?
Professor,
Yep.
is that to find any height or is that the maximum height or does it matter?
The maximum height it reaches above the launch point.
Okay.
Because at a different point in time, it will have some height, but it won't be at its peak yet. Does that make sense?
Yes. Thank
Okay.
you.
Yeah. Okay, yeah, that's right. Okay. Okay, so I have the time of flight written here. I have the maximum height above the launch point written here. Does it help? I just want to emphasize they have different initial speeds. All right, I got 21 answers. That's pretty good so far. If you're not sure and maybe you can narrow it down, try and take a guess at this point. Okay. I'm going to start to answer. I know not everyone has answered, but hopefully you're still thinking about it. Also, hey, if you ever decide you want to change your mind, you can always put that in the chat. That's totally fine. Okay, so in this situation, first of all, I'm going to say by far the most popular choice here is A. By far, that's the most popular choice. However, let's think about it real quick and see what is going on here. We're told they all reach the same height. So this is same for all. You know, for A, B, and C, it's all the same. Let's see, G is also the same for them all. 2 is the same for them all, of course. So then the only thing that, is free at this point would be V0Y. Well, that must be the same for them all as well, right? Because the left-hand side has to equal the right-hand side. So what's this telling us? Okay, if H max A is equal to H max B is equal to H max C, and I plug in this formula, then I see V0Y squared A has to equal V0Y squared B has to equal V0Y squared C. And in fact, because all of these are positive, in fact, all of the Y components of initial velocity have to match. Now, the Y component isn't the only component, but all the Y components have to match. So if we look at the initial velocity vector for A, V0A, its Y component is right here, V0Y, V0YA. That has to be the same as the Y component for B, and it has to be the same as the Y component
for C, because if they weren't, they wouldn't all reach the same height. Okay, do you agree about that point? Okay. Now let's look over at the time of flight formula, because we know now that the y component is the same for all. Well, g is the same for all, 2 is the same for all. Whoop. So the time of flight is going to be equal for all of them. Now, this was not a popular choice. Some people did pick it. Congratulations to those 4 people, but it was only 4 people. So, good for you if you got it, but it was not most of the class. So I want to see now, does it make sense at this point? Oh, come on, what is going on? Oh, okay, 2 more people have agreed during this conversation. So now it's 6 people. Okay, no questions? Is it clear now? Or is it not? Oh, it's not clear. Okay, it's not clear. All right, so the situation is this. We know that they all reach the same height. Yeah. Oh, how is Vy all the same? Okay, Vy is the V initial Y component is the same for all. But you can see, I think you can see looking here. Let me actually erase this piece on this side because it's maybe distracting. I think you can see that even though the Y components are all the same, the red and green and blue vectors all come up to the same height on my little Y-axis sketch there. Still, the length of those vectors isn't the same. Which is the longest vector from the red, green, and blue ones I drew?
Blue.
The blue one. So what is the largest for the blue one?
The X component.
The X component. Yeah, the X component is not the same for all of these. This is V0X for C, but V0X for B is shorter, and V0X for A is even shorter than that. So their initial speeds are different. They can be different because the X components are different, but the Y components aren't. And this is what this formula is telling us. This one right here is telling us that, in fact, their Y components aren't different. If they're reaching the same height, the only thing that matters to determine how high they go is what that Y component of velocity is. So that's how their Vy's can all be different, but their Vy's can all be the same, but they follow the different trajectory. They follow a different trajectory because the X components of velocity are different, which means the initial speeds are different as well. So they all reach the same height, but they don't all follow the same path. How come, you tell me, how come this one, C, can reach the largest range if they all have the same time of flight? How could C reach the largest range? They're all in the air for the same time.
The angle that it's shot from?
Yeah, so it's shot from an angle so that it's, it's shot from a lower angle at a higher speed. So that does play into it. Well, let's assume that V0XC is bigger. It's bigger than for the red and green cases. It's bigger than for A and B. But they all have the same time of flight. We're saying that they all have the same time of flight. Why does this one go the furthest?
Its X component is the largest, so it is moving the fastest in the X direction while also going up.
Right. So let's say it starts from the origin, then delta X is equal to X minus 0. Okay, so then we'll just say delta X is equal to X in this case. So then the distance covered in the X direction is this X component of the velocity times the time, right? If this is the biggest, even though the time is the same, that means the range for C, the distance covered by particle C, is going to be the biggest along the X direction. So the time of flights are the same. They will all land at exactly the same moment, but C is moving fastest in the horizontal direction. So it will make the furthest distance in the same time. Does it make sense?
Yeah. So in a airless environment, the lower the angle, the further it's going to go.
So it's not as simple as that. In this case, if you think about it, particle C has the largest initial speed. So that helped as well, right?
Yeah.
Yeah. Okay, so yeah, so if you think about it, if you had I hate to erase all this. Hang on, I can do that though. Hang on. Okay, watch this. If we go back to this case, if we had the same initial speed, then you can see that if you put a really small launch angle, like 15 degrees, actually the particle doesn't go that far. And the reason is because it's not in the air very long. It's in the air for only a short time.
You're starting to sacrifice the y component to be able to try to go
Right.
as you go to lowering.
Exactly. So 45 degrees is the sweet spot, right? But if we are launching at different speeds as we are in this situation here, where we don't have to sacrifice our height, we don't have to sacrifice our y component of initial velocity at all, then increasing the x component, that's just better. That would have the effect of lowering the launch angle, because you're lowering the launch angle as you keep increasing that x component velocity.
Okay.
So it depends on the situation, I guess is what I'm trying to say. Okay, now is it clear how they could all have the same y component of initial velocity, but their paths are so different? I got a thumbs up. Okay, but I only have one thumbs up, and the people who are on camera are looking defeated. Oh no, I got a couple more thumbs up. Can I please say it again? Okay, so actually, to the person I'm talking to in the chat, I'm trying to understand your question. It is the question, how can the y components of initial velocity be the same even though they follow different paths? Or is the question like the y components can't be the same for some other reason? Okay, well, while I wait, I'm just going to repeat what I was saying. They do follow different paths. That's absolutely true. I do not dispute that the parabola for A looks very different than for B than for C. I absolutely agree with that. But it is possible that they can all have the same y component of initial velocity. They have different x components. They have different x components. They are launched at different speeds and different angles. The one that's launched along path C has the largest initial speed and the largest initial x component of velocity. Even for the same time of flight, it's moving fastest along x, so it'll go furthest in the x direction in that same time. Particles A, B, and C are all going to land on the ground at the same moment, but they're shot with different initial speeds. Okay, unless I get a follow-up question, I'm just going to move on at this point. Is there any more questions?
Can I just ask a quick one?
Yeah, absolutely.
Yes. So when do you assume that the initial velocity is the same for all of them?
When you're told it. Here you're told it's different. But if you were told it is the same for all, then you should assume it at that moment. You shouldn't assume it unless you're told that.
And so with that, I can assume that the y component is the same for all of the projectiles.
Whoa.
The y component of the initial velocity.
Oh, okay, sorry, okay, all right, I got another question in the chat. So in this case, the y components of the initial velocities can all be the same, and yet they don't follow exactly the same path because they do have different initial speeds. If they didn't, and their y components are all the same, then their x components are all the same as well, and they all make the same parabola. So the question becomes a little bit boring, because then it would be, which one has the longest time of flight, A, B, or C, and you'd be looking at 3 graphs on top of each other. If the initial speeds are all the same and they all have the same y component of velocity, there's only one path they can follow here if they're all reaching the same height.
Okay, so it's just kind of like a balancing act because they were shot at different angle and also at different velocity, that it's kind of like balance it out. And when you say that they might have the same y component at initial velocity, you meant that it just kind of balances it out and it's almost the same. It might not be the same, but it's almost the same.
Sorry, what's almost the same?
Like the y component of the initial velocity.
Oh, okay. So moving back here, here's a case where they all have the same initial speed.
Okay.
But in this case here, where they're launched at different angles, then each one has a different y component of velocity. If the angles were very close, then they could have a similar y component of velocity, but it would never be exactly the same.
Okay.
Yeah. So the only way that you can get these different paths with the same height is if their initial speeds are different.
Okay.
Okay, and we're narrowing it down now. I got another question. I think I'm not following about how v0y squared equals v0 squared sine theta. So that I just want to like pop back because if one person has this question, probably several others do as well. Yeah, I'm just going to get rid of this stuff now, I think. And that's just to do with how the launch is initially. Anytime I have a launch velocity vector like this, v0 at angle theta, the magnitude of this is v0, that's the length of it. I always can draw this triangle. Here we go. And this is going to be the y component, v0y, and this is going to be the x component, v0x. Sorry, it's very hard to read. v0x. v0y is the opposite side. So maybe I back up a minute. Sine theta 0 would be v0y, the opposite side over v0, which implies that v0y is equal to v0 sine theta. And I can square that. Like I can square this, and it will still be equal. Okay. All right. I went past the question. Let me back it up. Okay, so 3 projectiles are launched with different initial speeds. This is a follow-up question. This is not the same question again. They're launched with different initial speeds, as we just established, so that they reach the same maximum height. List the projectiles. Oh, now, okay, I solved this question for you. This is a question, are you awake? If you're awake, answer it correctly. Okay, list the projectiles in order of increasing initial speed. Which one has the largest initial speed? I hope you know. After that whole discussion, I hope you know the answers to this. Oh, sorry, let me put the code back up in case you lost it. It's 7359416. 7359416. And you better get the right answer, guys. You better get the right answer. Yeah, same Mentimeter. Let me put it in the chat too. menti.com. And it's 7359416. Okay. List the particles from, okay, guys, I think this might be part of the problem. So if you're getting it wrong because of this, notify me in the chat. We're going from increasing initial speed. So that's, the order should be smallest initial speed v0 up to largest initial speed v0. So you want to rank them by smallest initial speed up to largest, not largest to smallest. No, that's fine. I am, okay, great. I am so happy if people are correcting this in the chat, because I'm standing here looking at it and A and B are equally popular and I'm panicking. Okay, good. No, okay, awesome. Thank you. Yeah, not largest to smallest, smallest up to largest, smallest initial speed up to largest. Okay, thank you. That makes me feel much better. Okay.
Need more coffee.
Yeah. But no, if you're getting it wrong because you misread how to answer it, that's much better than it's because you don't know. Okay. All right. Okay, I have a lot of answers now. Like I said, A and B are almost equally popular, but I think that's just an artifact of people swapping this around. It should go from A, the smallest launch speed up to C, the largest launch speed. Remember, they all have the same Y component, but they have different X components. So if you wanted to like put numbers to this, just to imagine, you could imagine that they all have the same Y component. V0Y is like 5 meters per second or something. You could put numbers to it, but then A might have, you know, an X component. Let me do it in red. A might have an X component that was, you know, 2 meters per second, and B might have one that was 3 meters per second, and C might have one that is 4 meters per second, right? So that what you see is that, you know, the diagram looked like before. If you find the total launch speed, you're going to do that by taking V0y squared plus V0x squared. And of course, that would be the biggest when you had the biggest X component. They all have the same Y component. Oh, hey, you don't see what I'm writing now. You don't see what I'm writing. Come back. Okay, there you go. This is just an example. Okay, an example with numbers. Okay. Okay, anyone unclear about it at this point?
Nope.
No, okay. And we can see that C must have the largest initial speed because it goes, or sorry, the largest X component because it goes the furthest. It goes the furthest in the same time. All right, now we derived an equation for max height, and now that we've done it, I just want to make it clear what it's not used for. Because if someone says, how high does this projectile go? Great, go ahead and use it. But if someone instead says, hey, how high was my golf ball when it passed over the tree? I mean, they're thinking like, you know, is it actually going to get caught in the tree, or is it really going to go over the tree? Suppose that you have an initial speed of 13.5 meters per second. You have a launch angle of 54 degrees. So they told you those things. The tree is 14 meters from the golfer. What do we not want to do? Actually, hang on. Thought I set this up as a. Sorry, guys, hang on. Okay, no. I just told you. What we don't want to do in this case, and I hope it's clear, what we don't want to do is use this equation. Okay, we did just derive it, and it seems like it should be a powerful equation. That the maximum height would be V0y squared over 2g, or equally, we could write that as V0 squared sine squared theta over 2g. We should not use that to figure out how high is the ball when it's over the tree. Is it clear why not?
Because it only tells us the maximum height.
Right, and we are not told that the tree is here. We actually, you know, without doing the calculation, we don't know where the tree is relative to the trajectory. So we should not assume the tree is in the middle, and we should not use the max height equation here. So how can we solve this one? We can go back to the kinematics expressions and work it out, okay? Now, it might not be obvious that this one is the one to use because you don't know the time here. What time is it when it's over the tree? How could I work out what the time is going to be when my ball is over the tree? How could I find that?
Oh, go ahead.
No, go for it, bro.
You use the X version of the formula and you just plug in the distance of the tree.
Beautiful. I'm going to use the X coordinate. So that the time is the parameter that links the motion in Y and X. So I can figure out what time it is here if I know how it's moving horizontally. And in this case, I do. I have the X equation. Delta X is equal to V0X times the time. I know that I've traveled 14 meters when I'm over the tree. So I'll be able to work out the time, okay? I could write this, hang on, let me go back a step. I can write this way too, V0 cosine theta times T. I'm just replacing V0X with V0 cosine theta. Why? Because I'm looking at, again, the same triangle, but V0X is the adjacent side. It's the adjacent side, so it's the cosine. And then I can rearrange this
the distance traveled divided by V0 cosine theta will be the time. I know that the distance traveled here is 14 meters. And I'm told V0 and I'm told the angle. So I'll be able to work the whole thing out. I can find the time, and from the time, I'll plug that into here. Then I'll be able to find the height. Yeah, and thank you, Aisha, as well in the chat. You're also pointing it out. So what this is here is a very standard kind of projectile problem where none of the equations we derived for, range or time of flight or height really fit here. But we just go back to our basic kinematics equation. Whoa, come on. We just go back to our basic kinematics equations and we can get everything we need. Okay. It's very common that you have to solve the y direction for a time and then put it into the x, or solve the x direction for a time and put it into the y. This is very common, very common. Okay. So actually, did anyone find the answer? I've solved the t part for you right now. Can you find the height? Just to remind you, V0 was equal to 13.5 meters per second, and theta, the launch angle, was equal to 54.0 degrees. I have someone answering me in the chat, but I have to actually double check it because I can't. I guess I could look ahead, but I can't remember what it came out to. Okay, yes, I agree with you. I agree with you, Michael. Okay. Okay, so where did this equation come from? I just got a question about this. This is also from the basic kinematics equations. Do you remember this equation here? V0 xt plus a half ax t squared. This is where it came from. Ax here though, ay is equal to minus g, but ax is 0. There is no acceleration in the x direction. So this term goes away and we're simply left with what's down here. That's all. Yeah, it's the x acceleration is 0. Okay. Yeah, so Michael put it in the chat for everyone and I agree with him. You can use the equation for the change in height over a particular time interval. We just plugged in the time here. The critical thing is, I put 9.81 here. Usually I use 9.8. You need to make sure that you don't forget the square in that second term on the t. This is one of the most common mistakes that I see, is that people are in a hurry on their calculator and they forget to punch that square. Don't forget to do that. Okay, don't forget to do that. So yeah, if you use 9.8 instead of 9.81, then you get 4.02. That would be the difference there. So if you got 4.02, that's okay as well. Now, somebody tell me, I'm only given 3 significant figures here and here. So I do give my answer to 3 significant figures. That's good. Why do I keep the time to more? Why do I keep the time to more significant figures? In fact, I could even keep it to 1 more, I think. Why am I keeping that time to more than 3 significant figures?
Because you would like to get more an accurate answer?
I would like to have a more accurate answer for delta y. If I trim the significant figures here early, time is not what I'm asked for. Okay, it's just something I'm using in the middle.
If I trim those significant figures early, then I'm going to get a less accurate answer. Okay, so I want to keep as many as I can. The other thing that you could do, but I think at this level, most people find it harder, is, you could even plug in this entire expression over here so that I'm plugging in the whole expression for the time and keeping it in algebra. That is something you could do as well. But I think most people find it a little harder at this point. Okay. I'm just,
So
that's an alternative, but.
So the
if you
safe
want-
bet is to only apply sig figs to your final answer.
Correct. And if you know you're going to answer is going to be 3, keep at least 5 in the calculation. If you know your answer is going to be 4, keep at least 6 in the calculation. If you know your answer is going to be 2, keep at least 4 in the calculation. I always keep at least 2 significant figures more, and then I chop it at the end. Okay. How did you know when to switch x and y to sine and
Yep,
cosine?
absolutely. Yeah, I was planning on being there.
Oh, sorry. Was that a question or did someone forget to mute?
I think he forgot to mute.
Okay.
Thank you so much.
All right. I'm muting everybody. Okay. Everybody's muted. Feel free to unmute if you have a question. So I have a question about how do I know how to go from this to the sine and cosine? Guys, this is really, I've said it several times, but I do want to say it again, because this is something that I do find people are genuinely confused by. What I'm doing is I have my X and Y axis, and I'm looking at the initial launch vector. Okay, so pay close attention, guys, because this is really important. This is the launch angle. Okay, I want to break this vector into components just like we did in the vectors lab. I want to break this thing into components. So what I'm going to do is I'm going to draw out a triangle right in here like this. This side here is the y component, v0y. That's the same on this side here. So v0y, this is the y component of the red vector v0. This is the x component, v0x. Okay. I want to be able to relate. I want to be able to relate the launch speed, which is the length of the red side, that's the hypotenuse, v0. I need to relate it to the length of the other 2 legs because those are my x and y components. So I need to break this thing down into x and y components. v0x is the adjacent side, so I take cosine theta is equal to the adjacent side over the hypotenuse, v0. Actually, let me write it. Let me write it out. Okay, so I'm going to take the adjacent side over the hypotenuse. That is v0x over v0. And what this implies is that v0x is v0 cosine theta. I'm getting this because I'm going into the component form. Okay, so I'm just looking at the length of that component, but I can write it in terms of the magnitude and the angle. So that's what I'm doing. And I'm doing the same exact thing for y. Sine theta y is the opposite side over the hypotenuse. The opposite side is the v0y. So what that means is that v0y is equal to v0 times sine theta, just multiplying v0 on both sides here, left and right, v0 sine theta, and that's my y component. Typically, you are given this angle, the launch angle. The launch angle is specified as the angle between the horizontal and how it's launched. This is the one you're typically given. But it's good, always practice. It's good practice to be able to draw this diagram and check the trig. This is always a good idea because occasionally in life, maybe you're given this angle instead. If you're given this angle instead, no problem. You will draw a slightly different triangle and you will proceed to do the same trig. Sorry, that's X now. And you'll still be able to work it out. Okay, so it's worth practicing that process of drawing the triangle, checking the trigonometry. For this case here, the way I drew this triangle, v0x would be equal to v0 sine phi, right? Okay, so it's not that cosine is always for x and sine is always for y. No, it comes from me drawing this triangle and applying some trigonometric functions inside the triangle. So it doesn't hurt to just practice that, practice. Always draw the triangle. Okay. All right, any questions about this example here? No, okay, good, all right, great. All right, what time do we have?
let's see. We have until 10:20, right? And then it's going to be, we'll break and go to the lab. Okay, so let's talk about this because we still have time, and that's wonderful. Yeah, whoops. Yeah, we're scheduled to, oh, it's scheduled until 10:25. Okay, we have till 10:25. All right, so we can put together our notions of relative motion and projectile motion into one picture and think about the different perspectives that a person might have on the motion. And actually, now that I think about it, if I can, I might set up a demo for you guys really quick, just at the start of lab to see this even better. So what we have going on here in this picture is we have a man, he's riding on a skateboard and playing with a basketball at the same time. And what he's doing is just dropping the basketball. Okay, so he's just dropping it. And when he just lets go of it, what he sees is the basketball just drops straight down to the ground in front of him, like you would expect for dropping an object. But the whole time, he's actually in motion. His skateboard is in motion to the side, relative to an observer that stands on the ground. Okay, relative to someone who's just a bystander watching this happen. Okay, the skateboard's in motion, yet the ball remains in front of him all the time and hits the ground and bounces. Okay, so it stays right in front of him. He can still kind of dribble this ball. What must this observer on the ground be seeing? Well, what she is seeing that the basketball doesn't drop straight down. That's what he sees relative to himself. It drops straight down. But what she sees is it follows a path like this, a parabola. It's a projectile. And why? Because when he releases it, he's saying, oh, I'm dropping it, from rest relative to my body. But relative to her, relative to the sidewalk, he's in motion with some initial speed v0. So are his hands, and so is the basketball when it's dropped. So from her perspective, what she sees is the basketball is launched to the side with an initial speed v0. And then it follows this parabola. Okay, so they both have different perspectives. Both are just as good as each other. He's moving to the side relative to the bystander. So, from his perspective, the ball is just staying in front of him and it's just dropping straight down. From her perspective, it's a projectile. Both are correct. Both are going to give the same time between its release and when it hits the ground. Both will work out the same. That both will work out that it's going to fall the same distance in front of the skateboard. Both will agree about that. The only thing
like
is
if
go ahead.
if you were, for another example, like if you were throwing a ball up and down in a car and somebody saw you go by.
Precisely. Yeah. So his frame is moving relative to hers. That's it. But yes, exactly. It's like if you throw a ball up and down in the car, you can still catch the ball just fine, but you're driving down the highway.
If somebody saw you from the street, they would see all of it going to the right as well.
Yeah, they would see it moving like a parabola from when you throw it to when you catch it again, because the car is moving along. Okay.
I have to ask, what textbook thinks that people ride skateboards while dribbling basketballs?
So this is from James S. Walker Physics, and you're right. I should have put a footnote for this picture, and I forgot to do it. So let me just write it on here. James S. Walker. I actually do recommend looking at this one too. I think this is a nice book. So if it's in the library, you could check it out. It costs money, that's the thing, but it is actually a nice book. It has some like relatively simple explanations, especially for energy, which is nice because a lot of textbooks don't.
Okay.
But yeah, so James S. Walker, whoever he is, thinks that this happens.
Well, it's a good example. It's just funny.
Yeah, it is funny. Okay. Okay. So here's an example. Bob, he's riding his skateboard, drops his ball when the skateboard is moving at 1.5 meters per second relative to the ground. What is the velocity of the basketball when it strikes the ground, measured relative to the skateboard and measured relative to the ground? Okay, so relative to Bob on the skateboard, I guess this is Bob's frame. this is Alice's frame.
Alice will be the observer standing still on the sidewalk, and Bob is on the skateboard.
Okay, try and see if you can work this out. We're told now the initial speed of Bob relative to Alice. That's the velocity with which Bob is moving relative to Alice. Let me just even label them here so it's clear. This is Alice. And here's Bob. This is 1.5 meters per second along the x direction.
So I will give it I hat. And we want to know what's the velocity of the basketball when it strikes the ground, according to someone riding on the skateboard and according to Alice's frame.
Oh, I'm going to have an overloaded situation. So I'm going to use lowercase b for basketball and uppercase B for Bob.
Actually, let me see what I actually did in the slides so I can match my notation. Okay, actually, you know what I did? I didn't even, let me change this because I'll match my notation. We're going to have S for skateboard and G for ground instead of Alice and Bob. Okay, so S for skateboard. And G for ground. So Alice is standing on the ground. This is the ground frame. And this is the skateboard frame. So I'm going to denote this instead, the skateboard's motion relative to the ground. Okay.
And so what we want to find is the final velocity of the basketball relative to the skateboard.
If you get it, just put it in the chat privately to me. Remember, relative to the skateboard, it's falling straight down.
Oh, and sorry, do assume this 1.25 meters, hey? Sorry, it's only in the picture. The height is dropped from is 1.25 meters. That's essential. You have to assume that. Okay, so in the interest of time, because I want to kind of try and see if we can wrap this up before the lab. So we want to find the basketball, how it's moving relative to the skateboard. So all of these things are for the basketball relative to the skateboard. Okay, and what we can see is that the basketball is dropping straight down relative to the skateboard. Basketball relative to skateboard, there was no initial velocity in the x direction. Relative to the skateboard, there wasn't. The basketball and the skateboard were moving together. Okay, so there's not. So that means the x component of the velocity in this frame is always going to be 0. So at all points later. But the y is not, because it's accelerating downward according to gravity. Okay, so what we find in the end is that when we put these together, the final velocity is going to be actually, do we want the speed? We want the velocity. Okay, so the speed is going to be the sum of the squares. So the speed here is going to be 4.9497 meters per second, because there was only the y. There was only the y component. That's it. So when you square it and square root it, I'm just going to get that. And then the angle, well, you tell me. Let's measure the angle from the x direction. What angle is it going to be moving at if it only has a negative y component? And that's it. Let me do it in a different color.
Straight down.
Yeah, it's straight down. You can parameterize this as, minus 90 degrees. You could parameterize it as 270 degrees, but that would be the angle. So now I have the magnitude and angle of the vector, or I could just write straight down. I could write straight down. And at this point, I'll round it to 5 significant figures, 4.95 meters per second down. Okay, or I could write minus j, or I could write at theta equals 270 degrees. Okay, something like that. Any of these would be fine. Okay. So Timmy, yeah, you got it spot on. Once it's moving relative, once it's going to be, let's change this now to, all right, so this is the answer for part A, okay, because I want to be able to wrap up. For part B, hey, look, I just wrote B over the top. Okay, now I'm going to find the basketball relative to the ground. Okay, that's what I'm trying to find now for part B. Now, this portion here stays just the same because the y motion is the same for both. Nothing has changed. The only thing I'm going to change is I'm going to write g here instead of s, but everything else is really the same. Okay, all the rest of this is the same. This is the part that's different, though. Relative to the ground, what is the initial x component of velocity?
1.5.
1.5 meters per second, and it's in the positive direction, the positive x direction. So now when I square it and add it to 4.9, roughly 4.95 squared, and take the square root, I'm going to get something bigger. Let me just do that right now. So I'm squaring 1.5 and I'm squaring 4.9497. I'm adding them together and taking the square root. Oh. And I am getting now, in the new case, I am getting 5.172 meters per second. I'll round that to 3 significant figures. 5.172. Now I actually would need to solve for the angle. No longer is the vector directly downward anymore, because it does have some forward motion as well when it's launched. So at this point here, it's the initial launch vector is to the side. The final vector here is going to have a component v0, vx, I should say. Vx is 1.5 meters per second, and the downward y component is minus 4.9497 meters per second. And so I can now find either this angle or this angle, either one. If I found that angle I would take the inverse tangent of 4.9497 divided by 1.5. And I would see that it was 73 degrees. So this angle would change. And I would write at 73 or at minus 73.1 degrees counterclockwise convention. Now you notice that I'm actually rotating clockwise, right? I'm actually rotating clockwise from X. That's what the negative sign takes care of. So in the counterclockwise convention, that means that if I turn clockwise, it would be negative instead. Could you write it as a vector with components? You could, unless it tells you magnitude and angle. Okay, if it doesn't tell you magnitude and angle, then it's true. For this case here, you could write it in the angle brackets, or you could write it as 1.5 I hat plus, or sorry, minus 1.5 I hat minus 4.95 J hat meters per second. And that would also be correct. Okay, that would also be correct.
For the angle, can you make it positive and say south of east?
Don't say south of east. Thank you for asking this question. Say downward from the horizontal. And the reason is because south doesn't point down into the ground. South is a horizontal direction. You see what I'm saying?
Yeah, those cardinal directions only matter if you're looking from a bird's eye view.
Right, and we're looking from the side here. So many people like to do this. They like to pretend south is down, but it's actually not, it's horizontal. So what I would say is downward from the horizontal. So 73 degrees downward from the horizontal. That's how I would quote that answer. Oh, and actually I have made a mistake. I was only given this number to 2 significant figures. So my answer should have been to 2 significant figures only. So I kind of cheated here, guys. I kind of cheated because I gave 3. Okay, you can figure it out. I want to get us to lab though now. Okay, so here's the nicer view of the solutions. This is for the skateboard frame, and then in the ground frame. That's the only thing that changes. Here I did give only 2.
A question.
Yeah.
So in the original function that you gave us that was in the slides, it's v squared equals initial velocity squared plus 2a and then times displacement.
Yep.
So how come here you can put final velocity squared?
How come I can put final, sorry, so when I start out with like this, are you asking why in this equation this is the final velocity squared?
Yes, because on the slides it doesn't say final velocity, it just says velocity.
Okay, guys, in the textbook, it usually omits the F, but that's what we mean. We mean the final velocity after it has traversed, after it has traversed
Oh, okay.
a particular thing. It's the same thing. I just put a subscript here for F and I didn't before, but it's the same thing.
Okay, gotcha. Thank you.
Some textbooks put the F, some just omit the F. I think the OpenStax book omits the F, but it's the same thing. Here I also use the vector addition between the 2 frames as well, to just include the effect of the skateboard relative to the ground. All right, let's take a break. This one you guys could look at your leisure. And if you get stuck on, you can ask me about it. We come back to it as a review if you want. But this one's just for you, for your practice, so you could try it out. And then this is what we talked about. So I will see you guys in the lab, but we went over. So let's take a 10-minute break. I'll see you shortly after 10:40 in the lab. Okay, so we'll start a little bit late. Take a 10-minute break before we go to the lab. Okay. All right. I'll shut the meeting down. I'll see you over in the lab.